Hello, I'm Keegan Williams, and this is my Physics 2211 lab on constant velocity. So to understand this lab, we first need to know some fundamental physics principles. Newton's first law states that an object at rest will remain at rest, and an object moving at a constant velocity will continue moving at that constant velocity unless a force is present. Our object should continue moving at a constant velocity throughout the course of this experiment. The momentum principle states that an object's momentum will change over time when a net force is present. The momentum principle can also be rearranged to get the position update and velocity update equations, which will be implemented in GlowScript to find the predicted position of the object after a time t. Below you can see these equations, along with the momentum principle. Before we dive into the setup and the breadth of the results, we first have to understand the purpose of the lab and the preview of the results. The purpose of the lab is to observe constant velocity in an object and then use the momentum principle to model the movement of the object using GlowScript code. Since there should be no net force, momentum should be conserved, meaning that we will find a linear relationship between the position and time, along with a constant non-zero velocity. Later we will see that the experiment adheres to Newton's first law and the momentum principle. The observed velocity of the object stays relatively constant over time. At the end of the trial, there will be a slight variation between the experiment and the model, but this can be attributed to slight errors that were not considered in the scope of this lab. Here's a tracker video that shows our object moving at a constant velocity. So before we started coding and analyzing data, we first had to understand the system and the surroundings. The system for this experiment would be the block. Everything that is not the block is considered the surroundings, so this would include the track, table, and the wall. After the initial push, there are no external forces acting on the system, so the net force during the movement of the object should be zero. Initial conditions and code implementation. The object starts from what is effectively zero and is given a push in the positive x direction. After the initial push, the net force on the object is zero. The initial velocity of the object was approximated as the average velocity of the object for the first 5 measured points. Below you can see how we calculated the average velocity and how we implemented it in code. Momentum principle iteration and code implementation. During the iteration of the loop from the initial time to the final time, the velocity is maintained as a value from the initial condition since the change in momentum over time is zero. To update the position of the object, we can rewrite the position update formula in GlowScript, where the final position is equal to the initial position plus the average velocity times the change in time. Position changes linearly since the velocity is a constant non-zero number. And to the left you can see a red box that highlights the code that does that. Here are results from GlowScript, which shows a linear relationship between position and time, a constant non-zero number for velocity, and a model which does represent what we determined from the tracker video. Details of the experiment. For the experiment, we first set up the track and block on the table. We made sure to orient the camera so that the block would appear to be traveling in the positive x direction. After pushing the block and recording the video, we upload it to Tracker. In Tracker, we hand-place coordinates over each frame of the video, which will create a table of data points relating position and time. After determining the initial velocity of the experiment as the average velocity for the first 5 points, I plugged the variable into GlowScript code as the initial velocity while also ensuring that net force was still zero. This shows the difference between the experimental and predicted position versus time. You can see that at the very beginning they start off the same and then over time they slightly diverge as the model becomes less accurate of our observed results. So after 3.2 seconds of movement, you can see that the models only differed by about 0.1 meters, which is a distance of less than 4 inches. This indicates that the model was an effective indicator of the position of the block in our lab. So sources of error in our lab may include human error from manually plotting the coordinates of the object in Tracker. The slight imperfections of the coordinate placement may have added up over time to skew the results of our data. Additionally, the experiment's differences in distance traveled when compared to the GlowScript model may indicate that the net force on the block was not perfectly zero. That minute variation may be due to imperfections of the track that might have caused friction, or possibly a slight incline on the track. Follow-up questions. What if the positive x and negative x axis were interchanged? If I were to flip the axis in Tracker, this would generate a line that has a negative slope. This would indicate that the object has a negative velocity from the perspective of the graph. In this scenario, the magnitude of the velocity would still remain the same though. Can we determine how many forces were present to get net zero force? No. While we know some of the forces acting on the object, such as the force of gravity, normal force, and kinetic friction, there may be small negligible forces at play that are not easily quantified. So while an exact amount cannot be determined, a minimum number of forces can be determined from what we can measure. Conclusions. In closing, we see that the position over a certain time of the experiment and model does not digress a substantial amount. This indicates that the velocities are very close to being constant and the same. The findings of the experiment reinforces Newton's first law, which states that objects in motion stay in the same motion when no net forces are present, and also the momentum principle, which states that an object's momentum will change over time when a net force is present. If the velocity were to change a significant amount that was not within a small margin of error, this would indicate that a net force was present. So through this law, we gained a deeper understanding of constant velocity and how an object can still move even if the net force present on it is zero.